So one of the most important things for the year that we've been doing is called stoichiometry. We started it way back when we first learned it by visualizing an assembly line. So for example, if you're making tricycles, you would say you'll need 3 wheels, you'll need 2 grips, maybe a frame, maybe some other stuff, and you make a tricycle. And so to imagine stoichiometry, to imagine the assembly line, you have to first imagine that you have these buckets that you start with. So there'd be a whole bunch of wheels in one bucket. You'd have a whole bunch of grips, whatever they look like, in another bucket, and you'd have a pile of frames over here, and you're going to assemble tricycles. So as you assemble things, you have to understand that the bucket's empty as you go along. So let's say, for example, well, if you look at these coefficients, these are called coefficients. This bucket here, I have to take 3 things out of, and then I take 2 things out of this bucket, and only 1 frame. That means this bucket is going to empty faster than the other 2 buckets. So these coefficients determine how fast these buckets get emptied, because those are how many you take out in order to make your tricycle. So let's say, for example, you started off with 99 wheels in this bucket, okay? And you had 100 grips and maybe 50 frames. Okay, so when do you stop making tricycles? Well, you stop making tricycles when one of these buckets is empty. So how do you calculate which bucket is empty? Well, the way you do that is you take one bucket and you compare it to the other. So here's how you show your work. 99 wheels. Let's see. If I wanted to use all 99 wheels, if I go 3 wheels for every 2 grips, then I can calculate that that requires 66 grips to use 99 wheels. This answer means 66 grips would be needed to use up all 99 wheels. How many grips are in the bucket? Well, there's 100. So I can use up, there are enough grips to use up all the wheels. So the wheels will empty before the grips do. Now let's do another calculation to see about the frames. 99 wheels, let's see, 3 wheels goes with 1 frame. That'd be 33 frames. 33 frames are needed to use up all the wheels, and you can see there was 50 frames to start with. So yes, all of the wheels will be used up. Okay, the wheels, when they're gone, I can't make any more tricycles. They call the thing that stops the assembly line, because one of the buckets is empty, the limiting reactant. Okay, it limits the products that can be made. So how can you apply the same thing to a chemistry situation? Well, you first need to start with that balanced chemical equation that gives you sort of the recipe. So let's say you had 4 irons, those are solid, and they react with 3 oxygen molecules, which is a gas, and that makes 2, let's say iron 3 oxides. Okay, and that's a solid. Now the fact that it's a solid, liquid, or gas doesn't matter for stoichiometry. So what you have to imagine is you have these buckets. Once again, in this bucket there's a whole bunch of these iron atoms. Okay, and in this bucket, I guess it'd have to be a box because the oxygen would leak out. There's all these oxygen molecules, and there'd be tons of them in there. Okay, and this bucket over here starts off empty because I'm going to take things out of these buckets and fill that bucket. So how do I do this? Well, the first thing I would do is take 4 irons out. Then I would take 3 of these oxygen molecules out. I would take them apart and reconnect them and put 2 things into this bucket, because that 2 means I put 2 in. So which bucket is emptying the fastest? The iron is emptying faster than the oxygen. The product bucket, the iron 3 oxide, is actually filling up slower than those are emptying. Okay, so how do you do stoichiometry? Well, you need to have some starting amounts. So let's say you had 0.152 moles of that, because in chemistry we count things in piles called a mole instead of individual molecules. Let's say you had 0.100 moles of that. So I will stop filling this bucket over here when one of these 2 buckets is empty. So how do you calculate that? Well, you pick one, doesn't matter which one, and so I'll pick the iron and say 0.152 moles of iron. It looks like I take 4 moles of iron out of that bucket every time I take 3 moles of oxygen out of that bucket. When I do that, that comes out 0.114 moles of oxygen. Okay, so let's see if we can interpret that. This number means in order to use up all of the iron that in this bucket, the other bucket better have 0.114 moles of oxygen in it. Well, it doesn't. It only has 0.100. That means I cannot use all of this iron because there's not enough oxygen in it. It means as these buckets empty, this one gets more and more empty, and this one gets more and more empty, but eventually this one is empty, and there's still some left over in that one. When this bucket is empty, I stop putting things into that bucket. Okay, what if I had picked oxygen to start with? So let's say I had 0.100 moles of oxygen. Okay, let's just cross this out. I'm going to come up with the same logical conclusion. That many moles of oxygen? Well, let's see. 3 moles of oxygen out of this bucket require that I take 4 moles of iron out of the other bucket. That comes out 0.133 moles of iron. Okay, let's interpret that again. That means for all of the oxygen to be gone, I better have 0.133 moles of iron in the bucket. How much do I have? Oh, I have enough. So this does happen. All of the oxygen, this bucket will be empty, and when it's empty, I will stop putting things in this bucket. In fact, I had 0.152 moles of iron when I started. If I used 0.133 moles in order to use up all the oxygen, I end up with 0.019 moles of iron left over. Okay, why did I do all that work? Because if the question is how much ends up in this bucket, I need to know which starting bucket emptied, so because that's when this process started. We've just determined that the oxygen is the limiting reactant. So all of this work was so I know to take the oxygen, the 0.100 moles of oxygen, and then I can say, let's see, 3 moles of oxygen. Take 3 out of that bucket. I put 2 into that bucket. Moles Fe2O3. That comes out 0.0667 moles of Fe2O3 that I produced. This process, when you use these ratios, it's called stoichiometry. When you use the coefficients of the balanced equation as whole number ratios, it's called stoichiometry. And we first had to determine which pile limited the amount of product we could make. And so that's what all of this work was for. Once we know that, it's almost like we can now start the problem and say, okay, that pile there, we stop putting things in this bucket when the oxygen bucket is empty. When the oxygen bucket is empty, we will have put 0.0667 moles of iron 3 oxide in the products bucket.